Hey guys, my camera just stopped temporarily on me there. I was just starting to solve this example. We're going to find the volume of the solid bounded by the cylinder x equals y squared and the planes z equals 0 and x plus z equals 1. To find that volume, I'm going to be calculating a triple integral over q of 1 times dv. So remember, volume is just a triple integral of 1, because if your density function equals 1, then you can view the mass and the volume as being the same. Okay? And my point with this integral, guys, is going to be that the z variable, right, is pretty easy to set up. It's bounded by 0 on the bottom, and it's bounded by 1 minus x on the top. Okay, so I'm going to put the z on the inside. What about the x and the y? Well, I'm going to draw a little picture here. I don't mind drawing two-dimensional pictures. X equals y squared is just a sideways parabola. Okay, and then if that parabola is intersecting the plane z equals 0, notice that x would be equal to 1. So x is equal to 1, this is, when z is equal to 0. So the region that I'm looking at is right here. And that's what I need to integrate. To do that integral, I think I'm going to, first of all, I want to find out where these points intersect. This is going to be 1, negative 1, and this is going to be 1, 1. You can figure that out by just setting x equal to 1 in the equation of the cylinder. And then you find out that y is either 1 or negative 1. Y is equal to plus or minus 1. I'm going to do the y variable on the far outside because I just want to integrate this direction, right? I just want to integrate from the parabola to the line x equals 1. So if I look at the y variable, I'm not integrating anything until I get to y equals negative 1. And then I'm going to integrate until I get to y equals 1. That would become my upper limit of integration. And now, between negative 1 and 1, I have to look in the x direction, which is to the right. I have nothing to integrate for a while, but as soon as I hit the parabola, that's going to be x equals y squared. That's my starting point for integrating. And I'm going to integrate until I get to x equals 1. There is the setup of the integral again. Okay, so on the outside I have dy, in the middle I have dx, and on the inside I have dz. This is one of the 6 orders of integration. Okay, and now I just have to do that integration, and that isn't too difficult. Of course, when I do the z integration, let me just show you what happens. So I leave the y integration exactly the same. I leave the x integration exactly the same. When I integrate dz from 0 to 1 minus x, I just end up with this integrand, 1 minus x, which I now have to integrate with respect to x and then y. What you might notice is that this is now a double integral that is calculating a volume for me. And it actually makes sense that that is the case. I'm going to actually draw this picture for you in 3 dimensions. Even though this would be kind of difficult to draw, I think it's useful to see it. Basically, you have this parabola x equals y squared sitting here in the xy plane. And what happens is the plane x plus z equals 1 comes along. Let's just say it's here. And that, of course, stretches in the y direction. And what happens is you get this kind of shape like this. It's kind of a little hard to tell what's going on. But there's this region in here. This is the region. This is the solid region of integration. It's kind of like you're kind of sawing off the cylinder at an angle and creating what kind of looks like a parabola-shaped wedge. That's what that solid is. Do you see that if you stand in the xy plane, let's say you stand somewhere here in the xy plane and you look above you, you start in the xy plane and you integrate vertically up until you get to the ceiling of this solid, which is exactly the plane x plus z equals 1. So if you had wanted to set this up as a double integral, the function that you would be integrating, the ceiling of this region, is exactly the plane x plus z equals 1. And that plane is what you're integrating in the double integral right here, right? When you solve for z, you just get 1 minus x. What I'm trying to say is that this volume can either be viewed as a triple integral or a double integral. When I view it as a triple integral, my integrand is just 1. But if I view it as a double integral, my integrand is whatever the surface is that is forming the ceiling of the region that we're integrating. Okay? From here, it's a pretty routine exercise to do the remaining two integrals. I think I will leave that to you guys. You can check it out. It's just a little bit of work with fractions. The answer comes out to 8 over 15 on this example. Okay. Hopefully this makes sense. So we're using a triple integral to do a volume in this case. Let's do one more example. The next example is going to have a little bit of a twist to it. So we're going to have to pay attention. Let me write it here. Here's an example. Let's evaluate the triple integral over q of dv. So that tells me right away that this is calculating a volume where q is bounded by y plus z equals 1, x plus z equals 1 in the first octant. I'm sure you guys know what the first quadrant of an xy plane is. The first octant is just referring to the part of 3 space where x, y, and z are all positive. Okay, so I'm going to actually start with a picture this time just to sort of show you the situation. Here's x, y, and z, and I'm only looking at this front quadrant that's right in front of us here on this paper. So what do we have? Well, we have the plane y plus z equals 1. Let me just draw that as a line in the yz plane, but then of course because it's in 3 space, it has to be stretched forever in the x direction. Okay? On the other hand, I also have the plane x plus z equals 1, and that is right here, and I'm going to stretch that one forever in the y direction. So I have these two crisscrossing planes, and I want to set up this triple integral. Notice that you can kind of see a square down here in the xy plane that is sort of formed by those crisscrossing planes. So you might think that this is pretty easy to just integrate x from 0 to 1 and y from 0 to 1. But there's a bit of a problem here, guys. And the problem is that if I, for example, choose to stand way over in this corner of the square and I look up above me, the ceiling that is above me, if I stand over here in this corner of the square, is the plane that's going this way, right? It's the x plus z equals 1 plane. So if I look up above me there, I see that plane. But now imagine I chose to walk over to the opposite corner of the square and I look up above me from that region of the square. Now the plane that I see, the plane that is, the first one above me, the lower plane in my view as I look up towards the ceiling, is the other plane. It's y plus z equals 1. And this is a problem, because if I set up my integral with x and y on the outside, I have to realize that the limits on z are not so clear-cut. It isn't like that picture I showed you at the beginning where we had, the triangle here and then another triangle here, and it was clearly this surface on top and this surface on the bottom, right? In this kind of a picture, it's obvious that you're integrating from here up to here. It's the same surface on the bottom and the same surface on the top throughout the region. But in this case, if I use this square as my region, I'm going to get into trouble because the surface that is quote-unquote above me, the first surface that I see above me, if I'm standing in that square, changes depending on where I am in that square. What I'm trying to get at is that the natural order of integration, which is to put x and y on the outside and z on the inside, is not going to be so effective in this example. I'm actually going to do something a little bit different. I am going to put x and z. Now the x and z domain is formed by this triangle. I am going to put that on the outside. Isn't that crazy? I'm going to put that on the outside, and then I'm going to put y on the inside. Of course, y is starting at 0. That's where the xz plane is. But now if I look up, and by up I mean in the plus y direction, which would be to the right, when I look up, I don't see the plane x plus z equals 1 at all. It's simply parallel to me. It's like if I stand in a room and I look directly straight up above me, I don't actually see the walls of the room. I'm only seeing the ceiling above me. So if I stand right here and I look in the plus y direction, right, the ceiling has nothing to do with this plane that's going forever in that y direction. It must be the other equation, which is y equals 1 minus z. Right? And again, so this means I'm doing y on the inside. As far as the x and z integral goes, well, that's pretty easy. The outer two limits of integration, remember I think of them as a pairing. X is just going to go, from 0 to 1 right here. I'll do that one on the outside. And then z is going to go from 0 up to this line. This line is, of course, just x plus z equals 1. And so when I solve that for z, I just get 1 minus x. So here we have the order of integration, dy, dz, dx. Okay. And again, this is quite a straightforward integration to actually evaluate, so I won't do it here. You guys can check that the answer is 1/3. Okay? So the order of integration, guys, we talk about this a lot. It's crucial that we think carefully about what order of integration to use. I can tell you that most of the time you're going to put z on the inside and you're going to integrate the x and the y on the outside. But I wanted to show you this example so you can see that there are situations where sometimes it's not so good to put the z on the inside. Okay, great. So let me kind of do something analogous to what we did when we were talking about double integrals a while back. I want to give you some tricks for evaluating triple integrals. And I think I'm ready to do that at this point. And we've talked about mass, we've talked about volume, we've talked about the different orders of integration, all of that in the context now of triple integrals. So what are some tricks for evaluating triple integrals? You may remember that I made a list of tricks for double integrals very recently. This list of tricks for triple integrals is going to look very similar to that. Okay? The first trick, we've already been talking about it, is to choose a favorable order of integration. Remember, it's a little trickier for a triple integral because you have 6 different possible orders. So you have x, y, and z that you can integrate in any order that you like. What the most favorable order of integration is depends heavily on the shape of the solid region that you have, as well as the function that you're integrating. Okay? Let's think about what else might be useful as a trick for evaluating triple integrals. Well, you might remember when we talked about double integrals that I mentioned symmetry. Symmetry can be extremely useful for evaluating triple integrals. Let me stop and just give you a quick example of that. Suppose I wanted to evaluate the triple integral of x dv over q, where q is going to be my solid, is bounded by z equals 4x squared plus 4y squared and z equals 4. Okay? Now, if you take a look at this region Q here, let me draw my xyz axes. By the way, z equals 4x squared plus 4y squared. I hope everybody recognizes that as your classic example of a paraboloid. And we're slicing that paraboloid off at the top where z is equal to 4. So z is equal to 4 is on top of this paraboloid. So this is your shape right here. Okay? If you look at that region, this is Q. Do you see that exactly half of it has positive values of x and half of it has negative values of x? The front half of the paraboloid exists in the region where x is positive, and the back half of the paraboloid has x values that are negative. Why am I looking at x? Well, look at what the function is. You're integrating the function x right here. So you're looking at the variable x, and you're adding up what x contributes to this triple integral throughout this whole solid. The point is that x spends just as much time being positive as it does being negative, and to the same amount if you cover the whole region Q. And for that reason, without even doing the integral, without even setting it up or evaluating anything, I already know that by symmetry, what's the answer going to be? It's going to be 0. Just by the symmetry of the region. We don't have to actually go to the trouble of evaluating that integral at all. Okay, so it's just 0 because of the symmetry of the region. Now, of course, our interpretation of this as a mass breaks down. Right? Anytime you are integrating a function that is sometimes negative, notice that for half of that paraboloid, x is negative for the entire back half. At that point, the interpretation of this triple integral as a mass completely breaks down. But we can still calculate the triple integral. And it just comes naturally, based on the symmetry of the shape, that this answer is going to be 0 without even having to do the work. Okay, I hope that makes sense. Feel free to again, stop and pause. Sometimes, instead of having a triple integral cancel out to 0, sometimes you can just do half of an integration, or a fourth, or an eighth of an integration, sometimes, depending on the nature of the function and the shape of the region involved. Okay? Finally, the third trick for evaluating a triple integral, and you saw this before as well, is going to be to use a nicer coordinate system. Use a nicer coordinate system. Okay. In the case of a double integral, we sometimes replaced our Cartesian xy integration with a polar integration using r and theta. In the case of triple integrals, of course, we're talking about 3D coordinate systems. And there are, as you recall, 2 of those. We have a cylindrical coordinate system, and we have a spherical coordinate system. And in some cases, the cylindrical coordinate system will be the most effective, and in other cases, the spherical coordinate system will be. Let me just remind you, for a cylindrical coordinate system, we're really just doing polar coordinates where we're tacking on a z variable. So z is just equal to itself, and x is equal to r cosine of theta, y is equal to r sine theta. Okay. Spherical coordinates, a little bit more involved, as you'll remember. You know, the formulas for x, y, and z are a little more intricate. You have this rho sine phi cosine theta for x, and rho sine phi sine theta for y, and rho cosine phi for z. This wouldn't be a bad time for you to go back and review these coordinate systems. We looked at this early on in the semester in chapter 11, and everybody needs to be able to work effectively with these types of coordinate systems. In fact, if you look at the example 2, where I used the symmetry on the paraboloid, there's a lot of symmetry along the z-axis there. We could actually use a cylindrical coordinate system to evaluate this triple integral. So in particular, what I would do is I would change the x to r cosine theta, right? My inside limit of integration would just be z, and you can see that z, if I stand somewhere below the paraboloid and I look in the z direction, you have some empty space for a while, but then you hit the paraboloid, which is 4x squared plus 4y squared, and you integrate vertically up until z is equal to 4. Okay? But then the xy region of integration is just this circle. And notice that, so if you set these two equations equal to each other, so if you set 4x squared plus 4y squared equal to 4, well, that just becomes a circle of radius 1. If you integrate a full circle of radius 1, theta will go from 0 to 2 pi, and r will go from 0 to 1. So this is setting up the limits of integration in cylindrical coordinates now. We're using a nicer coordinate system because we have a paraboloid here. The nature of the shape is suggesting to us that this would be a good conversion to make. Okay, so does everybody see that? If I just look in the xy plane, I'm just talking about the most simple polar region you could ever ask for. It's a circle, it's a full disk of radius 1. And that's coming from this equation right here. X squared plus y squared equals 1. So the limits of integration in polar coordinates are on the outside. The z variable is on the inside. I've replaced x with r cosine theta. And now I'm wondering if you guys remember that when you do this conversion to polar coordinates, or in this case cylindrical coordinates, there is a price you have to pay for doing that. And it's called the Jacobian. Sometimes it's this r dr d theta, but don't forget there's also a dz this time. Okay, so it's r dz dr d theta. All right, so that's how that would work. Oh, and I made a little goof here, didn't I? The 4x squared plus 4y squared needs to be converted into polar coordinates as well, so that would be 4r squared. Okay, so when I do the integration, okay, we can integrate z, we can integrate r, but the big thing to notice, guys, is that theta is being integrated from 0 to 2 pi, and the function that you're integrating, the only place you really have a theta consideration is right there, and sure enough, when you integrate the cosine of theta, you're going to get the sine of theta from 0 to 2 pi, and that is indeed 0. So by symmetry, we are going to get 0 for the answer. Great. Hopefully this is making some sense so far.